Okay, so let's do a little bit about capacitance. Um, when we've already been introduced to the parallel plate capacitor, it is a plate, or two plates rather, with charges on each plate. We have an equal amount of positive charge on this plate, a charge plus Q, and negative charge over here. And we know, of course, that creates an electric field that is uniform in the parallel plate capacitor. Now, outside the parallel plate capacitor, there are fringing fields. The fields kind of bend like this outside. We're generally not going to worry too much about that. But we've actually calculated the electric field from this particular arrangement of charges as sigma over epsilon naught, and in this case we've got the I hat direction, assuming this is x, this is y, and we'll let z be out of the page. So it's, yeah, that's the electric field in between the plates of the parallel plate capacitor. We know that we can calculate the electric potential energy that it would take to move a charge across the plates. We've done that calculation in the last chapter, and we put it in terms of the electric field. So the electric potential energy, let's say, to move a plus charge Q from plate A to plate B, A to B, like that. Um, and so this would be the minus of the work done by the electric force, which is equal to electric force dotted into dl. In this case, the L is just the pathway across the plate, and the force is Q times E. So it's just going to be Q, and it's actually E. Since it's dotted into dl, it'll be EX dx. The x component of the field is, in fact, sigma. So Q sigma over epsilon 0 times that distance. Let's call this plate separation here D. So that's what it is. In fact, I think when we derive this, we just called it QED, the potential energy in the field. So this is saying that the potential energy decreases as we move this positive charge. The potential energy decreases by this amount, minus Q sigma over epsilon 0 times D. So we can calculate the potential drop, which, remember, doesn't depend on the charge, as the change in potential per charge, that delta U, right? Delta V, we could call it, or we sometimes call it the potential from A to B. I guess call it like that because it's the potential at B minus the potential at A. And so this would be minus sigma d over epsilon naught. In other words, there's a potential decrease. The potential decreases by the amount sigma d over epsilon naught. In terms of the like the standard parallel plate capacitor, if I were to draw it like this, I have one plate like that, the other plate next to it like this. So there's a plus Q over here, there's a minus Q over here. Both of these have area A, so the sigma is the amount of charge per unit area. So I could write this in terms of Q over A d epsilon naught. And the capacitance, by definition, capacitance is the amount of charge we store divided by the voltage. Capacitance is what we're going to define as the ratio of charge to voltage. And so if we put in this expression for voltage, and by the way, let's go ahead, we can call it negative. It doesn't, the negative sign isn't really what's important here. Use the absolute value if you like. Q over Q d over A epsilon naught. So the Q cancels out, and what we end up with is A epsilon naught over D. So there's an expression for the capacitance. In other words, what this is the capacity of this parallel plate to have a voltage difference created by this particular charge separation. So the ratio of the charge stored on the two plates divided by the voltage between the two plates. And it depends on the permittivity of the material, which in this case is assumed to be just vacuum space, and the geometry, the area of the plates and the distance between the plates. Now, in general, what if we had a parallel plate capacitor with stuff in between? Like, let's say that we filled this up with stuff in here, okay? So we fill it up. What that does is that changes from free space, permittivity of free space, to the permittivity of whatever material that is. And we calculate or we characterize that permittivity by what's called the dielectric constant. Dielectric constant, kappa. Kappa is the ratio of the permittivity of a material to the permittivity of free space. So it's usually a fraction. I mean, it's a number that's typically bigger than 1, because the permittivity of free space is usually the lowest permittivity you get. And if that's true, the capacitance of a thing with stuff in it, we find that it's the same thing, except that we replace epsilon with epsilon naught, or kappa C0, where C0 is epsilon 0 A over D, the capacitor of free space. So this describes how much charge we can store in a capacitor. This is called a parallel plate capacitor. You can have a capacitor, though, in other arrangements as well. In fact, in most electronic equipment, you'll see a parallel plate capacitor. Let me see if I can pull it up here. That actually is like this. These are all capacitors in electronic equipment, and some of those could be in a plate arrangement. This one in the lower left could be a plate arrangement, but a lot of these, especially that one in the top, that's probably arranged like this. It's a capacitor that's coiled up, and it still probably has an insulating material in between it, so that the plates carrying the charges don't touch. But you could also have like a spherical capacitor. This would be something where you might have a set of spherical shells that are separated like this, with maybe a plus charge on the inside and a minus charge on the outside. Let's see, the shells, plus charge and minus charge on the outside, right? And so this derivation here that's in the textbook goes through that and develops how you can calculate the capacitance of such an arrangement. Use Gauss's law to calculate the electric field. You have the electric field then, which looks the same as an electric field from a point charge, because in between the two conductors, inside the inside conductor, you don't have any electric field. Outside the conductors, you don't have any electric field because the charge enclosed by the Gaussian surface is 0. So in between the conductors, you have this electric field that points from the plus to the minus radially outward, and it's just given by the same thing basically as a point charge situated at the origin. So the electric field looks like that, and E is equal to KQ over R squared R hat. So then if you want to find the potential difference between the two plates, V, you do the integral of E dot dl. Okay, so the dl here, we're integrating from R inner to R outer. This is R inner here, and then R outer is like that. The dl would just be dr, so you'd have this as kq integral dr over r squared from Ri to Ro, and that gives you a voltage of kq times 1 over R0 minus 1 over Ri, like that. So then to get the capacitance, which is Q over V, you would just do 1 over K, and then 1 over R0 minus 1 over Ri, like this. And so if I wanted to find a common denominator, first of all, the K, which is 1 over 4 pi epsilon naught, that makes the 4 pi epsilon naught appear. And then I would have R, whoops, wrote it capital, RO, Ri minus RO, so this would be 4 pi epsilon naught RO, Ri over Ri minus RO. And that's the capacitance from the from a spherical shell. So you can think of capacitors in other arrangements as well. A cylindrical capacitor. This one's of particular interest because you could also call it a coaxial capacitor with a plus charge here, a minus charge there. You can figure that out. I'm just going to write it down. Here's what you end up with. The capacitance of this arrangement is 2 pi epsilon 0 L over the natural log of R outer over R inner. You go through the exact same procedure to figure that out. So that's basically the theory behind capacitors. I'm going to skip over the next sections about capacitors in series and parallel. We'll do that at the end. But what I want to talk about here is, so a capacitor, let's go back to the parallel plate capacitor, holds charge separated, and there's an electric field in there. We said that there's potential energy in there. So there's energy that's stored in a capacitor. Well, what's interesting about this is that you might remember that the energy to move a plus Q charge from one plate to the other, we found that to be, or the change in potential as you do that is minus QED, okay, where E is the electric field in there. And you might think, okay, well, so that also represents the potential energy that's stored in the capacitor. That's not quite right. Another way of saying this is minus Q times V, okay? And so you might say, well, the charge stored in the capacitor should be minus Q times V. And this is the potential energy required to move this charge little q from plus Q to minus Q. But it is not the energy stored in the capacitor. Why not? So what we need to think about is, how did we charge up the capacitor? Okay, so in order to charge the capacitor, what we would think about is, all right, how do we, let's think about it like this. If we start out at the beginning, initially, how do I say that? Initially, we start with a capacitor that's uncharged, no charge. Now, in order to get charge on a capacitor, this doesn't quite make sense yet, but what we're going to have to do is hook it up to a source of charge. All right, that's called a battery. We'll learn about that soon enough, but let me just draw it like this right now. This is a positive terminal, this is a negative terminal, and we're going to hook up that to a battery. That's going to cause positive charges to flow onto the plate here and negative charges to flow onto the plate here. Okay, but we go from it being initially uncharged, Q0, to charge plus Q. And let's just say it goes in a linear fashion like that. Now, as it's done that, what we've had to do is move the charge from the battery to the capacitor in order to build up the charge. Okay? And so if we think about the work required to do that, the infinitesimal work is the voltage across the capacitor times the incremental charge it takes to move. But the voltage across the capacitor we have called Q over C, right? C is equal to V over Q. C is equal to Q over V. V is equal to Q over C. dQ. So that if we integrate this to get the total work, as we increase it from 0 to plus Q, increase the charge from 0 to plus Q, then this is what we find. And that integral there, the Q dQ, ends up being 1/2 Q squared over C, evaluated from 0 to Q, which gives us 1/2 Q squared over C. Okay, now, that's right. And therefore, that amount of work is also the energy stored in the capacitor. U sub C equals energy stored in capacitor. Okay? And so that energy is 1/2 Q squared over C. Well, notice that the charge on the capacitor is equal to V times C. So I could put that in there. 1/2 VC squared over C, which is also equal to 1/2 V squared times C. Okay? It's also, I could have used this relationship, V is equal to Q over C, and so I could say that the energy stored in the capacitor is 1/2 Q times Q over C, which is 1/2 QV. That's what's interesting, because you kind of expect that the energy stored in a capacitor might be Q times V. And it turns out it's not. It's 1/2 Q times V. Why? Because we had to go from 0 charge up to a final charge. And so the energy stored in the capacitor accounts for how the capacitor got charged. And so there's this factor of 1/2 that's not entirely evident why it's there. Interestingly enough, this also leads us to another sort of fundamental fact about electric fields, and that is the energy density. I'm going to write this as a small u. Energy density is the energy per unit volume. Well, if you look at this parallel plate capacitor, or the way that I drew it before, parallel plate capacitor, kind of like this, the volume here is going to be equal to A times D. And the energy stored in the capacitor, we called it U sub C. So I can write this then as 1/2 Q squared over C, and then over AD. Now, if I put that in terms of what I know to be the capacitance of a parallel plate capacitor, and let's just do one that's filled with vacuum right now, epsilon 0 A over D, I get 1/2 the Q squared, that's the charge stored, epsilon 0 A over D times AD. This D cancels out. The A gets squared, and so it's 1 over 2 epsilon naught Q squared over A squared. And so that's interesting, because Q over A is surface charge density. And so that's actually an expression for the energy density stored in the capacitor, but we can generalize that to be the energy density of any electric field. And so using the expression that we know for the electric field in the parallel plate capacitor, which is um, uh, right here, E is equal to sigma over epsilon naught, right? E is surface charge density over epsilon naught. I can write this as epsilon naught E squared over epsilon naught, and so this gives me this general expression for the energy density of any electric field. It's 1/2 epsilon naught times the electric field squared. That's really, really nice. It's really brilliant. And it generalizes to literally any electric field. Okay, well, there you go. That really covers sections 1, 3, and 4 of chapter 8. I talked about, except for the dielectric part, filling the capacitor with the dielectric. I did say that a capacitor with a dielectric has a capacitance that's increased by that amount right there. But note that if a capacitor has a dielectric material, which means basically an insulating material in between the plates of the capacitor, it changes also, since Q is equal to V times C. So then let's call, Q is equal to V times kappa C0, which is equal to kappa times V C0, which is equal to kappa times Q0. So it increases the ability of the capacitor to store charge. But what it does proportionately, let's look at the voltage. V is equal to Q over C, right? And so, excuse me, V is equal to Q over kappa times C0, which is equal to V0 over kappa. And so while it increases the capacitor ability to store charge, it decreases the voltage. It reduces the voltage by the same amount, this amount kappa, where kappa, remember, is the ratio between the permittivity with the dielectric in place and the permittivity of free space. Sometimes this quantity is also called epsilon r. You'll see it called this. This means relative permittivity. And so those are just values that depend on the type of material that you're using. And so different materials have different kinds of permittivity that would be given to you. Okay, that's enough. That's 1, 3, and 4. The molecular model of a dielectric, I'm going to let you read through that. That is pretty important because you want to see how a dielectric causes charges to shift in their configuration. But I'll do a separate video on capacitors in series and parallel because that's important to understand for where we're going.